Hello everyone, and welcome to my channel. This is a channel for educational purposes. We tend to look at theories of everything, all-encompassing theories, cosmologies, paradigm shifters, things that you can use for your awakening 5D consciousness, and otherwise use it for the benefit of your life, but you probably don't know about them because they're too obscure and have been suppressed. Today is our 439th video on the reciprocal system of theory from Dewey B. Larson. Larson was an American engineer and lived out in Portland most of his life, born in North Dakota in 1898, died in 1990. And around 1959, he proposed his two fundamental postulates about how the universe operated. And then through a process of deduction, he arrived at his theoretical universe, what his universe would look like if his postulates were correct. And then in some of his books, he compared his theoretical universe with the empirical universe of the scientists that they had measured in their laboratories and compiled in their tables. And in particular, he did this with chemistry in his book, Basic Properties of Matter. He came up with equations for many of the basic properties of matter and then compared them with the scientific tables that were present at the time. And we're looking at that book today, in particular chapter 4 on compressibility. And before we get to that, we'll just try to summarize the reciprocal system. It's pretty complicated, but it is way simpler than legacy science. In legacy science, you have to learn a different set of rules for every little pigeonholed subject. For the reciprocal system, you learn one set of rules and you can apply it to every subject. And Larson's reciprocal system is also known as the universe of motion. That's because Larson attempted to construct his universe based on motion. The universe is not made out of matter. It's not even made out of energy or force. It's made out of motion. And it's called the reciprocal system because for Larson, motion was the relationship between space and time. And there are a few caveats here. Motion in Larson's system was what he called scalar motion, not exactly the motion that you're normally thinking about, which is a vectorial motion, a motion that has a direction. Scalar motion is a motion that has no direction or no specific direction, really in or out. You can envision the surface of an expanding balloon. If you put a bunch of dots on the balloon, you can see that all of the dots are moving away from each other as you expand the balloon. And but they're not moving in any specific direction. Every dot is moving away from every other dot. And even the spaces between the dots are also moving away from each other. Every spot is moving in every direction. And so there is no specific direction. And the same is true if you suck in the balloon and it contracts, then all of the dots will be moving toward each other. Larson called these two motions the progression, the outward motion as the progression, and the inward motion as gravitation. And so for Larson, the universe is made out of scalar motion, and motion is the relationship between space and time. Basically, motion is a fraction with space or time as the numerator and time or space as the denominator. You can see that in the most basic aspect of motion, speed, the bicycle's moving 15 miles per hour, 15 miles of space in 1 hour of time. And if you double the speed, you can now say the bike is moving 30 miles per hour. Or, equivalently, you can say the bike is now moving 15 miles per half hour. You can multiply the space, or you can divide the time. That shows a reciprocal relationship between space and time in speed. Larson expands that to include all of our basic scientific phenomena. They are all forms of motion, and they are all relationships between space and time. But space and time and motion have multiple dimensions. He says 3 dimensions. So, the exponents of those fractions could be more than 1. You can have space to the 3rd power over time, or you can have time to the 3rd power over space to the 3rd power, which is matter. You can have time over space, which is energy, time over space to the 4th power, which is pressure. You can have space to the 2nd power over time to the 2nd power, which is momentum, and so on and so forth. So all of our basic scientific phenomena are relationships between space and time and can be expressed in fractions like that, which serves as a phenomenal check for equations to figure out whether they are dimensionally valid. And so space and time both have 3 dimensions. Larson, okay, now say you've got your expanding balloon going inward, your shrinking balloon, and there is no direction. All of the dots are moving toward each other, but in no specific direction. But now you decide that you're going to arbitrarily say that one of the dots is motionless. You're going to say that this is the reference point. This dot, I declare, is motionless. Well, then all of a sudden you have directions. You can impute directions to the other dots. They will all be moving toward that one dot. And it will appear as if there is a force field emanating from that dot, and that all of the other dots are attracted to that central reference dot. These are all functions of the reference system, not of the scalar motion, not of the motion, but of the reference system, of assigning a reference point. And that is kind of what goes on in both the spatial reference system and the temporal reference system. Larson refers to this as coordinate space and coordinate time. 3-dimensional coordinates, X, Y, Z coordinates. And so in our environment of the universe, we observe space as coordinate. We observe 3 dimensions of space in a still frame. We are space is still, and but we're moving through time. So we basically observe the universe as coordinate space, 3 dimensions of still space, and clock time, or a scalar motion in time. Time is always getting later and later and later and later, or farther and farther and farther apart. But it is not moving in any specific direction. So that's a scalar motion in time, but a coordinate or vectorial motions in space. And so that coordinate space is very much like abstracting the universe or picking a reference point. We are anchored to a spatial reference point. And so the the reference system, the spatial reference system that we're seeing is very limited. In fact, the 3 dimensions of space only take up 1 dimension of motion. And in Larson's postulate, motion, space, and time all have 3 dimensions. So our reference system is very limited in what it can express. It can really only express 1 dimension of scalar motion. Now, if we were in a different environment in the universe, we would observe the reciprocal of that, which is that we would observe coordinate time, 3 dimensions of time in a still frame. This is the temporal reference system. 3 dimensions of time in a still frame, and progressing space, or scalar space, clock space. Space is always getting farther and farther and farther apart. And this happens in what he calls the cosmic sector. And the cosmic sector is an outgrowth of another one of Larson's first postulates, is the discrete unit postulate. That is that space, time, and motion are all quantized. You have to have a full unit of space or time or motion in order to have any of those things. So if you don't have a full unit, you don't have squat. You have nothing without a full unit. It's just like with many other things in the universe. You know, you don't say go to the tree and pick me half an orange. That's absurd. You either get a whole orange or you don't get any orange, or you get 2 or 3 or 4, but you don't get 4.5. Now, once you take the orange off the tree, I suppose you can cut it in half or whatever, but it comes only in full units. And the same is true of space, time, and motion. Now, space, the unit of space is approximately 1/500,000th of an inch, and the unit of time is approximately 1/6.5 quadrillionth of a second. 6.5 times 10 to the 15 units of time per second. And now, if you have unit speed, would be a combination of those. Remembering that speed is space over time. So speed would be 1 or 2 millionths of a second, 2 millionths of an inch per 1/6 quadrillionth of a second. That turns out to be the speed of light. So the speed of light is what Larson calls unit speed. That is 1 unit of speed, which is approximately 3.3 times 10 to the 8 meters per second. And that is what Larson calls unit speed, and that is the background motion of this universe, Larson's universe. In Larson's universe, the universe of motion, you have to be able to conceive of motion without anything that's moving. Motion precedes the thing that's moving, and that is what this unit speed progression is. So we have unit speed outward at the speed of light in all directions. That is what Larson calls the progression of the natural reference system. Okay, so he has a spatial reference system with coordinate time and clock space, or coordinate space and clock time. He has a temporal reference system of coordinate time and clock space. And then he has a scalar reference system, or the natural reference system, with it, which is just 1 unit of space per 1 unit of time. And that is the expanding balloon progressing in both space and time. And he calls that the progression of the natural reference system. That's the 0 point of Larson's universe. That is the source of all matter, and everything else in the universe comes from that source. And that's the empty universe. That's the universe where you don't have anything. When you don't have anything, you still have the ever-present, omnipresent, and eternal progression of the natural reference system. And that is also the boundary or the midpoint of the universe. So this is where Larson makes his measurements from, and it also means that half of the universe is moving faster than the speed of light, and half of the universe is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector. And in the cosmic sector, you have coordinate time and clock space, and in the material sector, you have coordinate space and clock time. Now, within each of the material and cosmic sectors, you have a subregion that has to do with the discrete unit of time in the cosmic sector and the discrete unit of space in the material sector. In the material sector, you have atoms and particles and molecules that interact. And when they do interact in less than 1 unit of space, then they don't interact in space because there isn't space in less than 1 unit. And so if you don't have space, then you have to have time, because the universe is made out of space and time, or motion. And so it has to be one or the other or both. If it's not space, it has to be time. Larson refers to this as the time region, and this is the region of atomic interactions and molecular interactions in the material sector. The same is true in the cosmic sector, but with in less than 1 unit of time, you have cosmic atoms and cosmic particles and cosmic molecules interacting. And they interact in what's called the space region. And cosmic atoms are otherwise known as antimatter in legacy science. So legacy science does know something about the cosmic sector, but very, very, very little. Einstein's dictum was that the speed of light is the maximum speed of the universe. In Larson's system, the speed of light is the midpoint of the universe. And so atoms come about from basically taking that outward motion of the progression and through first vibrating it in 2 dimensions and then rotating it in 3 more dimensions, you end up getting atoms. And you end up getting that progression, which is in 3 dimensions, motion in 3 dimensions. You basically turn it back, and it now becomes that contracting balloon. So the expanding balloon of the progression through rotation and vibration becomes atoms, which are gravitating. So they are on that contracting balloon of that earlier example. And so for Larson, matter doesn't just have 1 number for its period in the periodic table. Each element has 3 numbers: 1 2-dimensional rotation, 1 secondary 2-dimensional rotation, and or the A number is the primary 2-dimensional rotation, the B number is the secondary 2-dimensional rotation, and the C number is the 1-dimensional rotation that is in the opposite direction. And the first 2 numbers alternate, and the third number is optional. It can be 0 in the noble gases, and it can be positive or negative. So that's what Larson's periodic table looks like. Now, also in the material sector and cosmic sector, when you cross those boundaries into the inside regions, into the time region and the space region, you have to invert again, just like you do when you cross the boundary of the speed boundary, the unit speed boundary. So in the time region, the progression is moving inward and gravitation is moving outward, which is the opposite of what it was in the outside region. So this eventually causes the interatomic equilibrium between atoms, because the progression, which is moving inward, is constant and omnipresent, whereas gravitation is variable based on an inverse square law. And so there is a point different for every atom, and even within atoms, different orientations of atoms, they establish a different equilibrium point where gravitation and the progression are the same. And that's where the equilibrium is established. Larson measured those and came up with equations for those in the first couple chapters on interatomic distances. Now we're on chapter 4 on compressibility. So this is the rate of compression. Now the internal pressure is caused by the progression. The progression is always there, and so it's called internal pressure. It's always there. And that is bringing the atoms closer together. But the rotational forces or the gravitational forces of the atom are resisting it. And those forces get activated more and more the higher the pressure becomes. And then there can also be an external pressure coming from outside the system that can force the atoms closer and closer together as well. So Larson comes up with various expressions or equations for various permutations of the compressibility here in this chapter. And we're going to just let him go here, and we'll see. I'll try to clarify, but we'll just try to get a feel for what Larson's talking about here. Furthermore, we're in the middle of the chapter, toward the end. We might even finish today. Furthermore, we are able to show that the slope of the last section of the experimental curve for each element is identical with the theoretical slope determined by the calculated maximum values of the internal pressure, and the slope of each of the intermediate sections is in agreement with one of the possible intermediate values of that internal pressure. Now, Larson sets up the curves for the compressibility are in line segments, basically, because at certain critical points, the atom or the molecule has inflections based on first-order transitions and second-order transitions. The first-order transitions are the result of a changing of the crystal structure of the atom in the solid state, which is like the interatomic equilibrium, which really has something to do with orientation of the atom, and then also, the second-order transitions have to do with the atom bringing more of its rotational forces to bear in opposing the pressure. Because pressure is a two-dimensional thing, whereas the matter is a three-dimensional thing. And so the amount of pressure kind of depends on how the atom is oriented. If the whole atom is kind of resisting it, there's going to be less force than if like just a little bit of the atom is resisting it. So at certain pressures, the atom will begin to employ more and more of its rotational forces against that pressure. That is at least the way I understand it at this point. My understanding of this is evolving. Okay, an exact theoretical definition of the curves will have to wait for further progress along the lines discussed earlier. In the meantime, the amount of the theoretical information already available will serve as a means of testing the validity of each set of empirical results and will also enable a reasonable amount of extrapolation of the compression curves beyond the present limits of the shockwave technology. Back in the early 20th century, like the maximum that they could really produce was about 100,000 atmospheres. But now in the 80s, when Larson was writing this, they were arriving at this shockwave technology, which could get up to several million atmospheres. So this is currently filling in a lot of the, maybe theoretical gaps in our understanding of compressibility. Table 20 is a comparison of the theoretical volumes based on empirical reference volume for each of the sections of the curves as in the preceding tables, with the shockwave results obtained at Los Alamos on the elements that were investigated over the widest range of pressures. Unless there is an increase in the compression factors in the vicinity of 100,000 atmospheres, the compression curves established on the basis of Bridgman's measurements extend into the lower range of these shockwave experiments. In these cases, the theoretical volumes up to the first change in the compression factors are calculated on the basis of the reference volume selected from the Bridgman data, and no reference point is identified in this table. Okay, so he's looking at the shockwave compressions in this table. He gives the AZY numbers, which are very much related to the ABC numbers of the atomic configuration, or the atomic factors for Larson's periodic table. And then he gives the initial pressure, or the initial pressure is 1. Interatomic distance cubed is basically the initial volume. And then due to pressure, the volume contracts. And so, for example, I think he's looking here at gold. Gold at the first pressure, which I'm not sure how many atmospheres that is. It looks like it's 100,000 atmospheres. The calculated value is 0.972. The observed value is 0.970. And he comes up with the same type of results for tungsten and molybdenum, or however you pronounce that. And then he's got goes to higher and higher and higher pressures. When you get up all the way to 1 million atmospheres, gold is all the way down to 0.610. He calculates it at 0.610. The observed value is 0.612. And gets all the way up to, looks like 2 million atmospheres. Doesn't have gold in here for that though, but yeah, so this table has several different atoms, several different molecules or atoms, and it has a large range of different pressures, all the way from 100,000 up to 2 million atmospheres. And it looks like Larson is pretty much always very close to the observed value. Certainly within 1% of the value in, it looks like pretty much every case. He's, 0.748, he's got 0.747. 0.779, he's got 0.780. 0.768, he's got 0.768. So, however Larson's doing it, he's able to get a pretty accurate result as far as the shockwave results of these extreme high pressures. Okay. A rather surprising feature of these comparisons is that the agreement between the shockwave results and the theoretical volumes is as close as the agreement between Bridgman's static values and the theory. Bridgman is the early investigator that that did this way back in the early 20th century. And so Larson's agreement with the shockwave values is as close as his agreement of Bridgman's, even though Bridgman's values only went up to 100,000 atmospheres. It is true that this set of measurements was deliberately selected for the comparison, and it represents the best results rather than the average. But in any event, the close correlation is a significant confirmation of the validity of both the shockwave techniques and the theoretical relations that he developed, Larson. The question that now arises is what course the compressibility follows beyond the pressure range of this table. In some cases, a transition to a smaller base volume appears to be possible. Copper, for instance, may shift to the rotations of the preceding electropositive elements at some pressure above that of the tabulation. Aside from such special cases, the factors that determine the compressibility in the range below 2 million atmospheres have reached their limits. At the present stage of the investigation, however, the possibility that some new factor may enter into the picture at extreme pressures cannot be excluded. A collapse of the atomic structure of the kind envisioned by the nuclear theory is, of course, impossible. But as matters now stand, we are not in a position to say that all aspects of the compressibility situation have been explored. It is conceivable that there may be some as yet unknown capability of change in the atomic motions that would increase the resistance to pressure beyond what now appears to be the ultimate limit. Now, keep in mind that he says that that's impossible for the nuclear collapse because Larson doesn't believe in the nucleus. He believes that the atom is the nucleus, and that all of the electron cloud around the atom, that is the space between the atoms in the interatomic equilibrium. Some shockwave measurements have been made at still higher pressure levels, and these should throw some light on the question. Unfortunately, however, the results are rather ambiguous. 3 of the elements included in these experiments, lead, tin, and bismuth, follow the straight line established in Table 20 up to the maximum pressures of about 4 million atmospheres. On the other hand, 5 elements on which measurements were carried to maximums between 3 and 5 million atmospheres show substantially lower compressions than a projection of Table 20 curves would indicate. The divergence in the case of gold, for example, is almost 8%, but there are equally great differences between the results of different experiments, notably in the case of iron. Whether or not some new factor enters into the compression situation as pressures above those of Table 20 will therefore have to be regarded as an open question. Okay, that's the end of the chapter, and just to pep you up, that is the hardest chapter of any Larson book that I've ever read, is that particular chapter, at least for me. That's why it took us 12 days to get through it, but now we're through it, and we're headed on to Chapter 5, which is on heat. So the other aspect of this interatomic thing, heat and pressure. So heat, coming up next. Thanks for tuning in.